Okay, so we were studying AC potentiometers, and one particular kind of AC potentiometer that we have seen is called polar potentiometer, which uses what is called a phase shifter. Okay, there is one more type of AC potentiometer which we will study, but today we will not be able to finish that. So today I will take up a smaller topic, easier topic, which is called Kelvin-Varley potential divider. It is named after Kelvin and Varley. I'm not sure about my spelling. Okay, so first, suppose we have a potential divider, which is nothing but series connected resistances. This side we can apply an input voltage V in, and here suppose we tap it from here. Here we will get some output voltage. For simplicity, if this is R and R, then this voltage will be exactly half of the input voltage, right? Okay. Now suppose we want to get a voltage which is 1/4 of the input. Can we do like this? Can we take one more potential divider which divides the voltage in two halves? Okay, so here the voltage will be half of this voltage. Now if I connect these two in cascade, then this is also RR, say, will this voltage V out be 1/4 of V in?
No, sir.
No, absolutely right. So this will not be equal to 1/4 of V in. It would have been so if we could put a buffer or something so that no current is drawn from here. In that case it will be 1/4, but in this connection it will not be 1/4. So how much will it be? Let me leave that as a homework. You can do it. Okay, acha. Okay, so today we will learn a scheme with which you can divide a voltage in, say, 10 parts or 100 parts or 1000 parts, something like that. Suppose you want to divide a voltage in 1000 parts. Okay, so what one could do, one simplest way is to take 1000 equal resistances. So many you need, I mean 1, 2 up to 1000 equal resistances, and then you can tap from here to get 1/1000 parts of the input voltage, or you can tap from any other position to get any multiple of that. But then you need 1000 such resistances, a cumbersome arrangement. We won't like that. Okay, rather suppose if we can make a simpler arrangement which is like this. Suppose 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this arrangement can divide the input voltage in 10 parts. Okay, Achha, now suppose I take one more such arrangement, and then this also can divide a voltage in 10 parts, and then I can take one more similar arrangement. This can also divide a voltage in 10 parts. And if it were possible that say I connect them in cascade somehow, so that this input voltage V in is first divided into 10 parts, then this will divide that voltage into even more 10 parts. So here we will get 1 upon 100 of the input voltage, then we divide that again, and then we will get 1 over 1000 that fraction here. In that way, if it were possible, it would be nice, because then you see we need only 10, 10, 10, 30 total resistances, not 1000. 30 is much less than 1000. You can even think, okay, we want to divide it into 10,000 parts. Then if you go for a one chain, single chain, you need 10,000 resistances. But now we can cascade, say, 4 such dividers, and we will need only 40 such resistances. Okay, so that will be much easier to deal with. But will this arrangement actually work in that way? No. Why not? Because of this fact. When you cascade 2 potential dividers in this way, if this is dividing the voltage alone, if it is dividing in 2 halves alone, this is dividing in 2 halves, when you connect them into together, they will not give 1 upon 4th part of the input voltage. So this way here we will not get 1 by 1000 times V in. It will not be so. Okay, but it would have been, yes please.
Sir, means instead of using so many resistances, means in one chain, can't we use a potentiometer? Because if you use a potentiometer, then so many resistances won't be used, as in potentiometer voltage is directly proportional to the length, so you can slide along and get those required voltage, and then we can use numerous potentiometers like in chains in the same manner, and then we can get, means the idea means
see, this is also a potentiometer. This one chain is, it is a what is the difference between this and the long wire we have studied here? Only difference is that, yeah, here you can vary it smoothly, here you can vary it in discrete steps. Okay, that's the difference. The smoothness is not there. But this is also a potentiometer. Basically, you think this as a long wire, okay, and from where you tap, that is your like the jockey attached to the galvanometer. This is also called a potentiometer. This is just a discrete thing, so no difference at all. Okay, now the thing is that you were possibly saying that in a potentiometer we can vary it smoothly, but then also there are problems. Problem number 1, suppose you want to divide some voltage in 10,000 parts, then your scale should be also marked with 10,000 divisions, and each division should be of not infinite semal length, of some finite length, which you can visually take the reading from. Okay, so, and also that will be a long arrangement, big arrangement. But when we go for a discrete set of resistances, then you can pack it into a small box. Okay, but if it were a long piece of resistance, that will be a bulky arrangement. We won't like that. Okay, so does that answer the question, the point you raised, or I bypass that?
Yes sir, okay sir, understood.
Okay, fine. So the main problem here in this scheme, we wanted it to behave like, oh, the first chain will divide the voltage in 1 by 10, next 1 by 100, next 1 by 1000, but that will not be the case. Okay, so Kelvin and Varde proposed a very genius idea that is like this. They said, okay, instead of taking 10 resistances, let me take 11 such resistances. And apply the V in here. So let me number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then here these two ends they are connected in this way. Okay, so you can slide this thing up or down, but when you do that, if this junction is touching, say, junction number n, this will touch n minus 2. Okay, so the gap between this, I mean this end and this end, will always be two resistances. You can say slide it up wherever you take it. So it will, if it is touching this this junction, this will touch, I mean n minus 2th junction. Okay, something like that. Okay, then after that, here also we will take 11 resistances instead of 10. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and in the final one, we will use 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here also we will use this kind of arrangement. Okay. So you have to move the two ends together, not one end alone. Okay. Acha. Next, acha, if all these resistances are say R, etc. Okay. We will choose these resistances in a way. Acha, let me not call this R. I will. Okay. Let me call this R first. Okay. Now I will choose the value of these resistances in such a way that the total resistance from here to here, all these 10 resistances, okay, that will be equivalent to two resistances here. So that means all these 10 resistances together will be equal to 2R. Okay, so that means how much this resistance should be? So in total this should be equal to 2R. So how much this one alone will be? 2R by 10, that is R by 5. This will also be R by 5, R by 5, R by 5, etc. Okay. If so, now you see the beauty of this scheme. Okay. Consider, suppose this voltage is V1. From here to here. Achha. Then how much voltage will we have between any two adjacent terminals in this segment, say between this point and this point, this point and this point, etc. So what is the voltage difference between two adjacent terminals? That is the question. Okay. So acha, tell me what is the total amount of resistance between this point and this point. Total resistance.
So 11.
No, not 11R, because you
10R.
have this also in
Oh.
parallel to this.
10R.
10R.
10R, exactly 10R, because this is 2R and this I have chosen to be 2R. So 2R parallel 2R will become 1R. Okay, so although there are 11 such resistances, but actually it is equivalent to 10R. Okay, that is the beauty. If so, then how much is the voltage between these two terminals? In terms of V1, it will be V1 by 10, right? Here V1 by 10, here V1 by 10. And how much is between, say, this terminal and this terminal? Anyone?
Same.
V1 by 10. So here we are getting V1 by 10. Okay. If so, now if I take the output from say here, between these two terminals, then how much voltage is here? This voltage is V1 by 10. So how much is this voltage? So here it will get divided by again 10 parts. Okay, so in 10 parts, so V1 by 10 again divided by 10, we will get V1 by 100. Okay, exactly V1 by 100. Okay, so that is the beauty. Now suppose if you want say 5 V1 by 100, then we can take the output between say this point and 1, 2, 3, 4, 5, this point. Between this and this we will get 5 V1 by 100. Okay, something like that. In the same way, so the idea was we have chosen these resistances to be 1/5 of all these resistances. So in the same way, now look backwards. What do you think these resistances should be? If I want to get finally here 1000 divisions, 1000 parts of this input voltage, we will take it to be 5R, all of them. If so, then you see what happens. So how much is the total resistance from here to here? Anyone? From here to here, how much is the total resistance?
50R.
50R, exactly. Okay, because here we have 10R. Okay, here we have 10R. This 10R is in parallel to this 5R and 5R 10R. So this two parallel with this will become 1 5R. Okay, therefore total resistance is 50R. And if so, then between any two adjacent terminals, the voltage is V in by 10. And from here to here, we will also get V in by 10. Okay, so here we will give V in. Between these two, we will get V in by 10. Okay, no matter wherever I put this, I can slide it up or down. If I can put it here, wherever I put it, I will get V in by 10. And then, so that is V1. V1 is equal to V in by 10. And this voltage is then divided again in 10 parts. Here we are getting V1 by 10. That means V in by 100. Okay, and then here that will again be divided into 10 parts. So now each part here is V in by 1000. Okay, we are getting exactly 1000 divisions. Okay, that is the nice thing. So now, if this part is okay with you, let me ask you one question. Suppose I want V out to be say V in by something like this, say 0.345 V in.
So can you scroll your page a bit up?
Yes. So I want the output voltage to be input voltage multiplied by 0.345. How can I get that? Let me tell you. What I will do is this. Okay. I will take first this as my reference. 0 volt. Okay.
Sir?
Yes.
Sir, means are there always three chains in the Kelvin bridge, or there can be multiple?
There can be 4, 5. If you want further divisions, you can go up further. No problem. Okay. I am demonstrating with 3 only. Okay. So now I will take the for output also I will take this as the reference. I mean one terminal of the output, okay, where the other terminal will be, that I will show. Okay, let me make it little smaller. Okay, fine. Now I want the output to be 0.345 times V in. What I will do is this. I will slide this slider up to 1, 2, 3, up to this point. Okay. So like this. So let me erase the wire and put it here. Okay. So what is the voltage at this point? What is the voltage at this point in terms of V in? It will be 1, 2, 3. 3 upon 10 parts of V in. So this point is at 3 by 10 V in. This point is at 3 by 10 V in. So that means this point is also at 3 by 10 V in. Okay. Next 4. Next digit is 4. What I will do, I will move this slider up to 1, 2, 3, 4 here. Okay. Then these wires will also move up. Okay. So how much is the voltage from here to here? From here to here, how much is the voltage? Here the total voltage from here to here is V in by 10, which is divided again by 10 parts. So individually here to here we have V in by 100, V in by 100, etc. So from here to here we will have 1, 2, 3, 4. 4 by 100 V in. So this point is at 4 by 100 V in. Can you visualize that? Okay. So this point is at, with respect to this, this point is at 4 by 100 V in. But this point is already at this voltage. Okay. Let me write it in a simpler 0.3. That's easy. 0.3 V in. And now from here to here, this voltage is 4 by 100 means 0.04. 0.04 V in. Okay. So what is the absolute potential at this point? Absolute potential at this 0.34. Absolutely. 0.34 V in. Okay. Fine. Then I need this third decimal, which is 5. So I will go 1, 2, 3, 4, 5 at this point. Okay. So from here to here, voltage difference is V in by 1000 multiplied by 1, 2, 3, 4, 5, which means 0.005 V in. However, the absolute potential of this point is 0.34 V in. So if you add 0.34 V in plus this quantity, the absolute potential of this point will be 0.345 of V in. With respect to which point? This point, ground point, reference, or this point. So between these two terminals, I will get 0.345 V in. So this way we can get output voltage as any fraction of the input voltage accurate up to 3 decimal places. Okay, idea is clear?
Yes,
Sir,
sir.
so I joined a few minutes late. Can you tell me why we can't use like three of such, like three such, what do you call them? Like
Potentiometer.
sets of resistances,
Yeah.
three such sets of resistances, and do the same arrangement without using this this particular arrangement?
I mean, without
What will be
this.
the problem?
Without.
Without that slider.
Okay, so that's what we started with today's topic. So suppose we have just consider this part, okay, left side, okay, R. So here, if this right side is not there, we will get V in by 2, right? If this, I mean, let me disconnect. So here we will get V in by 2. Okay. Similarly, if we take another similar potential divider, whatever voltage we give between this terminal and this terminal, half of that will come here. But if we just cascade them normally, I mean just join them with a wire, this voltage will not be V in, the input by 4.
So can we not use a buffer between the two?
Yes, if we use a buffer, then it will be V in by 4. But if we do not use a buffer, then this will not be V in by 4. Yes. Then we need to use a buffer.
So means, we are avoiding buffer, means is it costly or something, means that that we are avoiding using buffer? Because
I
if
would
we
say it's costly. What I guess, this name of Kelvin, they were long back. Before transistor
And probably
electronics.
op-amps were not even discovered at that.
Yeah, so these things were much before those days. Yeah, that is the idea. And also now still now buffers are there so easily available. But still, one beauty that is still there in this arrangement is that we do not have to rely on non-linear electronics. One aspect of precision measurement is to avoid non-reliable things as much as possible. Although op-amps are not that unreliable these days, but still, suppose you start with, you make the first electronic device in your company or in your lab. You have to validate that against something. What can you validate that with? For that you need something simpler like this.
Sir, means in this arrangement, the number of chains we use, and we will get that number of accurate decimal places after point, right? Means if we use
Yes.
3 chains,
Then up to 3 decimal you can go. If you need up to 4 decimal, you have to use one more phase, or whatever you call this. Okay, and then in this phase you will need 11 resistances. Last one will have 10 resistance.
yes.
Okay. So let us stop here today. Thank you all. See you next week.